Let's go. Okay, negative mass today on extraordinary concepts in physics. So this is something that I've wondered about. Isn't really mainstream physics, but it's kind of cool to think about. So you've stumbled once again onto extraordinary concepts in physics, sometimes called Physics X, where I'm trying to go through some of the more interesting concepts in physics and focus on the concepts and not on the math so much. It was pointed out that you can get the lectures a number of places. They're on iTunes, they're on the web, but you can also get the slides on the web. This was pointed out to me that it might not be obvious that all the slides in extremely high resolution, so you can actually read this by going to Starship Asterisk Physics X and find that, and then on each of the lectures has its own little place, and there's all the slides in high resolution. So go get it if you want it. So, negative mass. It's one of the golly gee whiz topics of physics. So it's one of the things that isn't really taught in undergraduate physics or even graduate physics, but it's fun to think about. So let's talk about, but physicists have debated this for a while, so it's a relatively mature topic. It's not something like, oh, no one ever thought of that. Oh, no, people know about it. But here's what it is not thought to be. It is not dark energy, which we covered in other lectures. It's not antiparticles, which is a common misconception, that if you could have the antiparticle of an electron, which would be a positron, that would have negative mass. It is not thought to have negative mass. Actually never completely tested, but not thought. Negative mass is not demanded by any grand unified theory which would combine E and M with the weak force and the strong nuclear force. It is not detected in any abundance whatsoever. So there is no present indication that actual negative mass exists. It's hypothetical. It's fun to think about, but don't get the impression that we have this stuff in the lab and we're holding out. No one's got this stuff in the lab. It's fun to think about right now. It is not prohibited by general relativity. General relativity is an inclusive theory. Things are allowed in there that you might be surprised about. However, they're not seen in reality, and you can put negative mass terms into general relativity. It is not thought to occur, I guess this goes with the other one, as point particles. So this is hypothetical, fun to think about, isn't actually there so far as we know. So there are three attributes a negative mass point particle might have, even though we don't think they exist. One, thinking about inertial mass. So when you move, you have inertia, which means that people need to watch out because you could bump into them and deflect them in some way. So the inertial mass of a negative mass point particle would have the momentum in the opposite of its motion. So if you bump into a wall, let's say you wake up one morning and you find yourself composed of negative mass. And then next thing you do is you run along and bump into the wall. The wall does not move in the opposite direction, it bumps toward you. So it has, you give it the opposite momentum than you thought it would have. It's interesting to think of things in terms of gravitational mass. So a negative point mass particle would have what's called active gravitational mass, which means it would repel. So let's say you woke up one morning and you had a lot of negative mass and you found yourself the mass of a star. Then you would want planets like all your other friends, but you would find that you have negative gravitational attraction toward them, and so you repel them, so you can't have normal planets, unfortunately. However, you will find yourself that you could yourself go in orbit around the sun if you were relatively low mass, because you were attracted to a positive mass particle. So that's part of the equivalence principle. So if you wake up and you have negative mass, you would still be pulled toward the floor. You wouldn't be anti-pulled. So attributes of negative mass. F equals ma would hold. I've played with this stuff a little bit. Force becomes confusing. Better to focus on acceleration so you know which way things go. This is just the gravitational formula, which says that Newton's laws, okay, so negative mass, you don't have to get into general relativity. You can play around with it pretty much with Newtonian gravity. You can use just the Newtonian thing. Again, you're better off probably thinking about acceleration terms instead of force terms, because you can go nutty trying to figure out which way the force goes. Okay, so negative mass can do some really strange things. Here's some of the really strange things. Let's say you had a positive mass, positive point mass, and that and a negative point mass. So here you have a negative. This is not charge, this is mass. Here's a positive. So the negative mass would, the positive mass would attract the negative mass. So then this thing would want to go here because of the gravitational field of this guy. The negative mass would repel the positive mass. So then positive mass would then be repelled from the negative mass in this way. Together the two would do what's called run away. So they would not stay there. They would go away in the opposite direction of the positive mass, and they would just accelerate. Zoom. Zoom, they're gone. So once you call your friends to say, look, I've got a pair of positive mass, negative mass, by the time your friends get into the room, it's gone. It's accelerated probably up to near light speed. So what would stop it from accelerating? So far as we can tell, nothing. It would just keep going. However, if they were to hit the wall, are we creating free momentum and free energy here? Is this a way to create? All we have to do is create negative mass, put it near positive mass. They would run away, and we would have a perpetual motion machine that would generate a tremendous amount of energy. Would this work? And the answer is no, because the negative point mass has negative momentum and essentially negative energy. So it will cancel out the other thing. So if they both hit the wall of the room, one's going to push the wall out, the other's going to pull the wall in. They're going to have no net effect. So the net momentum and the net energy would cancel in runaway pairs. However, you can try to come up with a basis for interstellar drive, as Robert Forward has. He's a recently deceased physicist who's written a lot of science fiction, a lot of really fun science fiction. So you can look up some of his. One of the thing that I've been most remembering that he's written is something called Dragon's Egg, where there's beings that grow up on the surface of a neutron star, and they live much faster. But it's really cool. But he was a real physicist, and he's contributed to physics in many ways. And he came up with the diametric drive, which theoretically could propel a spacecraft across the universe if we had negative mass, which we don't. In playing with this, you get into strange arguments. Okay, you want the two masses to remain the same, right? So if there's usefulness in having the two masses be the same and not have the two masses run away from each other, if, for instance, in creating a diametric drive. However, it's actually difficult to try to create a connection between the two. If you just try to connect them with a rod, strange things could happen because it would pull and push in strange ways. So even if the masses have unequal magnitudes, so you have a big plus and a small minus, you can still get them to move in strange ways such that energy and momentum are conserved. So they won't necessarily run off together, and this guy would then impact the wall while having much more, so you've created free energy. No, that's not going to happen. So whatever energy this hits the wall, and momentum this hits the wall with the same magnitude of momentum, and so it's not going to affect it very much. There are times when things act like they have negative mass. And one of them most commonly in the universe is something called a void. So if you have a universe with all kinds of matter in it, this matter is usually broken up into, well, there's dark energy we heard, but let's consider now just baryonic matter with atoms and molecules. Then you will have these atoms and molecules attract each other, and they will form clumps. You will get high density regions and low density regions. What's really interesting is that you could start out with, just through a statistical fluctuation, having a low density region. And this low density region will act effectively as a negative mass in the sense that it will repel effectively the stuff around it. And so you will have a nearly spherical, well, it would be if everything else was uniform, shell moving out, and you would get lots of things that would accumulate on the shell. You would get mass accumulating on the shell. And the inside region here would be called a void. So voids that just are created in the universe by chance, they don't just go away. So they're more than stable. They expand. So there's a whole field of study as to what happens to voids in the universe. These voids, however, they aren't truly negative mass. First of all, if you consider all the mass in them, they're all only made of positive mass. It's only the relative amount of mass that makes it act like it's negative mass. Second, the voids don't themselves follow the equivalence principle. All right. Every now and then, I've seen a couple of papers, I should have dug out a reference on this. Someone gets the idea that there's ways to detect negative mass. Now, there's no negative mass in the laboratory because we would have noticed, or at least not in any of the laboratories that happen to run physics experiments. But let's say you had stars made of mass out in the negative mass out in the universe, and they were floating around the universe. Maybe they would produce photons that would look just like normal photons, and we wouldn't know. However, a common thing that it's been discussed in other lectures here is gravitational lensing. So a normal gravitational lens, let's see if I can get the right colors here. This is a lens, and this is a source, and this is an observer. So normally, light from a source would go out and would be pulled to an observer by the positive gravitational lens effect of the lens. Therefore, sources actually are amplified on the sky, and they appear bigger. There's more than one light path that goes. However, if you had a negative mass here, instead of a positive mass, negative mass lens, you would have a source here would have its photons deflected, and actually they would appear angularly smaller on the sky. Therefore, in normal gravitational lensing, when you have a positive mass lens move in front of a background object, you get an amplification of light. Looks like this, roughly. However, actually, let's do that in red. Let's clear that. Undo. So positive lens, hello, all right. Positive lens gives you a light curve like this, where this is time, and this is brightness. However, a negative lens would have, oops, see, I keep trying to do this. Here we go, undo, go back to blue. A negative lens would have a star having a certain brightness, and then it would drop down. I don't know the exact shape of the curve. I'm assuming it's like that. So one could look around for cases where background stars would become dimmer, and we see them. But every time we see them, we can attribute it to an eclipse of another star. We've never seen a light curve that exactly matches what you would expect from a negative mass lens moving in front of a star. So once again, this says it's a fun concept, but there's no indication that real negative mass exists in measurable amounts in the universe. Okay. However, dark energy, which we know is different, has a repulsive gravitational effect on normal matter, but it has a positive mass energy. So that exhibits something different called negative pressure. As given in other lectures, examples include cosmic strings, domain walls, and the cosmological constant. A local variant is called the Casimir effect. Briefly mentioned in the lecture on virtual particles is that some virtual particles can be thought as having negative mass. This is cool. So some virtual particles you can't detect them because they disappear before you can find them. However, negative mass is ultimately the reason for attractive forces, why you would have gravitation attract or opposite charges attract. Ultimately, it's put on the virtual particle level with negative mass particles that disappear. It's different than another case called faster than light normal matter, which would be something completely different but won't be really covered here in much detail, although we'll mention a little bit in future lectures, imaginary mass. And with that, I will wrap this up and see you next time. Bye.